This is going to be the first video in a series where we will be looking into real analysis. Throughout this series, I will be repeatedly using examples and definitions from the textbook called Mathematical Analysis: A Straightforward Approach by K.G. Benmore, 2nd edition. So, real analysis, in a very broad sense, is the study of real numbers and their properties. Before we actually look at real numbers specifically, we should understand the concept of sets as well as set notation. So whether or not you have worked with sets in previous mathematical courses, this should be a good refresher or an introduction. So a set is a collection of objects which are called its elements. So in a very simple introduction, we can say that some element X or some object X is inside of a set. We'll use this symbol, and we can call this set S. So we would read this as X is an element of, and then the set name S. So I would say X is an element of S. All this means is that X is inside of the set, and we'll look at that more specifically in a second. If I take another object, let's call it Z, and I want to explicitly say that Z is not in the set S, and I can say Z is not an element of S. So this symbol here, with the slash through it, is the negation of the first one. So this not an element of, and I guess we can put these in quotes. So X is an element of S, Z is not an element of S. And what is S? What does that mean? What does it mean to be an element of a set? Let me define a set. We'll call this set C. And I'm going to call it C for colleges. I'm not going to use any mathematical concepts right now. And how we define a set is we use a capital letter for its variable name. And then we use an open curly brace. And we'll say that this specific list of colleges, I will just take Vanderbilt, Yale, Harvard, and UPenn. And then we ended off with a closed curly brace. So this is my set. And a set can be defined however you want. So this is just a custom set that I have. So my set C has the elements Vanderbilt, Yale, Harvard, and UPenn. So if I were to ask you, is University of Miami an element of C? The answer would be no, because the University of Miami is not in this set. Vanderbilt is an element of C. Yale is an element of C. Harvard is an element of C, as well as UPenn. So typically when we work with sets, we're not going to have, large, names and words like this for the most part, at least in this course. But I could say that Yale is an element of C. I could say also University of Miami is not an element of C. That is the entire basis of a set. Now, one thing we should know, so I'll get rid of these down here. The simplest way of just specifying a set is listing its elements explicitly, just like we did here. If we want to use numbers, I'll call this the set A. My set A has the numbers 1/2, 1, square root of 2, e, and pi. And again, we close it off with a curly brace. This is my set A. 0 is not an element of A. 73 is not an element of A. Pi is an element of A. All we're doing is defining what is and what is not inside of my set. There is no meaning to my set A. It is just some numbers I chose. In the future, we will have explicitly defined sets, such as the set of real numbers, the set of natural numbers, or the set of whole numbers, or the set of integers. And we'll define those later. So, we can be a little bit more broad in our sense of defining sets. So looking at set A, I have explicitly defined specific values or numbers that I want in my set. But what if I want a set of all positive numbers? How would I express that? Because it wouldn't really be feasible to say, write out every single positive number, right? Theoretically, I guess you could say that, you could start listing a pattern like 1, 2, 3, ... But what about, numbers like 1.3 or 1.072, right? Those are all still positive numbers. So how am I supposed to list all those? So what we can do is we can be a little bit more definitive in our set notation. So I'm going to get rid of all of this. What we can say, we can define another set. We'll call it S again. I'm going to say my set is going to be equal to all values x such that, so we use a colon for such that. You may also see it as a long bar. So my set is all the values x such that that value x is greater than 0. Another way you might see it also is S is equal to the set of all values x such that with a long vertical bar x is greater than 0. Both of these mean the same thing. These are the same. It is really up to convention. Throughout the series, I might use both. Personally, I typically use the bottom one more naturally, but they both mean the same thing. So if we were to break this down, my set S contains all values x. X hasn't been defined yet. They contain all values x such that my value x is greater than 0. So if I were to ask you now, okay, is negative 3.003 in S? Would that be a yes or a no? Right, because I haven't explicitly defined a set with negative 3.003. But remember, my set S is equal to all values x such that x is greater than 0. So is my number greater than 0? No. So I can say that negative 3.003 is not an element of S. Any positive number, any positive real number really, will be in this set. Now, we can also define something called the empty set. The empty set. The empty set, as you may probably guess, is a set with nothing in it. And I'll call this set D. And we define the empty set not with curly braces, but with just a simple symbol. Looks like an O with a slash through it, or a 0 with a slash through it. Some people also write it as 2 curly braces with nothing in it. Something like that. Formally, this is what we'll be using, but you may also see it with the 2 curly braces. That's totally fine as well. The empty set is basically a set with nothing in it. So a great example of this is the set of all values x such that x squared plus 1 equals 0. So remember, we're doing real analysis. So obviously there are 2 complex solutions to this equation. But since we're in real analysis, there is no value x such that x squared plus 1 equals 0. Therefore, this is equal to the empty set. And the empty set's pretty, it's used a lot in set theory. We'll be using it a lot. But just know that, as long as you can read sets like this, you'll be pretty much golden. So again, to reiterate, we would read this as, and I don't have to define this, right? I don't have to put A equals, right? I don't have to. It really doesn't matter. For this, I'll leave it out. So this set right here is the set of all numbers, all real values x. And again, in real analysis, x is assumed to be a real number. So this set is all values x such that, okay, the colon, such that x squared plus 1 equals 0. Well, that would mean that x squared equals -1. And there's no real value that, there's no real value x that gives us a solution to this equation. So therefore, this would be the empty set. That's all we're saying here. So we can also say, we can work with 2 sets. So I'm gonna get rid of the left side here. We can work with multiple sets. So we'll say let S and T be sets. And again, we use S and T, they're capital. Sets are always capital by convention. If we want to say a set contains another set inside of it, we call them subsets. And I'll explain what that means. If S is a subset of T, we write it as S is a subset of T. This means that every element of S is also in T. So for example, if I have a set S equals 2 and 4, and I have another set T, 1, 2, 3, and 4, we can see that every element inside of S exists inside of T. So T has a few more elements, that's fine. 1 and 3 are in T as well, but we can see that all of S is contained inside of T. So therefore, we can say that S is a subset of T. Now be careful. This symbol looks a lot like the element of symbol, but this is not the same thing. So do be careful. It's missing that line in the middle. So don't confuse those. Now, this is, the basics of just sets in general. In the next video, we'll be looking at the set of real numbers, and that set will be used throughout the entire course. So we'll give a pretty formal definition for it and see some conventions on how to work with it.